Hello all and welcome back to this course on digital systems. In the last lecture we looked at the analysis of sequential circuits where we started with a circuit diagram and went to state equation, state table and a state diagram. Now we are going to do the reverse. Okay, so we are going to look at design of sequential circuits. Design of okay. So to set the context, we will pick the example again which is given in the textbook, right, where we are looking to detect a sequence of three ones. Okay, so basically what's going to happen is I have something here, okay, some, let's say, like a random bit generator which is going to output some x here, and this is going to be a sequence of zeros and ones. Okay, for example, this sequence could be 0 0 0 1 1 0 1 0 1 1 0 1 1 1. Okay, this is the idea, and what we want to essentially do is to make sure that we flag, after this bit has come in, that we have now seen a sequence of three ones, right? Clearly you see that until now, right, until this point, a sequence of three ones has not arrived yet, right? So for example, after this 1 1, unless I get the next one, I'm not sure that I've seen the third one, right? So therefore it's exactly at this point that you should be saying that yes, the sequence of three ones has been detected, and once you're done with that, of course you could go, suppose you have another one here, then this is another sequence of ones, right? Or you could go back to 0 and then start all over again, right? So essentially this is the the general idea of a sequence detector. So the sequence detector is an application of that. We are going to use the sequence detector as the example to highlight how to design a sequential circuit. Okay, so let's begin with this. Okay, so given this description of the problem in English, right, and maybe an example like this, the idea is now to take this to a state transition diagram first. Okay, transition diagram. Okay, so now let's go back and look at this first now. Okay, so the first thing is the flip-flops, right? Obviously, by the way, before we even get into that, it's quite obvious here that I need a sequential circuit. I cannot do this with a combinational circuit because I need to know what the previous state of the system was. The input that came earlier, I need to keep track of that, right? And therefore, this kind of functionality cannot be achieved by pure combinational circuits, right? Because when the next one comes, you have no idea if the previous input was a 1 or a 0, right? You have lost that state in a combinational circuit. So therefore, when we talk about a sequential circuit, we always have a flip-flop. Invariably, you will have to talk about a reset state. Okay, so we will just call this state as S0. In fact, you can call it a reset. reset state. Okay. So the idea here is you can give these states any names. Okay. Now, and then you can move to the other state. Now what you are doing is the flip-flops, so basically the idea is, remember, what we are trying to do eventually is to figure out this X, right? And I also have Y, the combinational block here. Okay, this is my combinational block 1, combinational block 2, right? So you basically take this, feed it here, and you get some output Y here. Okay, so essentially this is the, so what we want to do is we want to figure out what this combinational block 1 and what this combinational block 2 should be in order to tell us, in order to implement this particular sequence, right? So if you look at it, really, if I just isolate this system out, there is an input X, there is an output Y that we are looking at. The internal flip-flops, the states, all that stuff is immaterial to us, right? That's why these states can be any, you give it any names, and then you have to, of course, translate it to some binary values, right? But these are all hidden states and we don't care about these, exact state transitions and how we implement, whether we are using a D flip-flop, JK flip-flop, all that doesn't matter. As far as the user is concerned, we are just seeing X and Y, okay? So, starting from the reset state, if the input happens to be a 0, then you remain in the reset state, okay? It's like, you got a 0, so there's no 1, so you cannot proceed to the next state at all, right? Now, on the other hand, if you do see a 1, right, I'll go this way, okay? The input is a 1, then I go to, I'll call it state 1, okay? That means I've seen 1, 1, that's what it means, okay? And then I'm going to say that, of course, the output from this guy should be a 0, okay? Remember that the output Y need not be a function of the input, because as soon as you reach the state when you have seen the 3 ones, you have to output a 1. So all that matters is the output is a function of only the states of the flip-flop, okay? And therefore I will put the output, mark the output in this circle itself. Output has to be 0, okay? And then I move to state 2, okay? And this is 1. I mean, this is also thing. What this means is, after now, when you are in state 1, if you see a 0, right, then you basically have to come back to the reset state. So if when you are in state 1, it means you have seen 1, 1, and if you see a 0 after it, you go back to 0 because you are starting from scratch again, right? And therefore you go back there. Now from here, if you see another 1, you go to state 2, that's an input 1, right? Again, from the state of seeing 2 ones, if you see a 0, you obviously have to go back to the 0, okay? And finally you move to at state 3, that means you have seen 3 ones, you can output a 1 here, okay, and right, so this is a 1, right, and you have seen a 1 there and therefore you just remain. Now at state 3, there are 2 things that can happen. You can get a 0, that means you go back to the reset state. 0, okay, and if you see another 1, okay, it means you are going to continue to be in the state 3. Why? Because you saw 3 ones here and now you are continuing to see another 3 ones here, okay. So if I take this sequence 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, right, this is my x, okay. Maybe I'll take that to the next page, right. Okay, this is my thing x, and now I'm going to tell you what my y is, okay. Y is obviously, you know, you are in state initially is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and finally you see a 1 and again a 1 and then you're back to 0. Okay, so this is how the output y will look like, and if I look at the states, right, so now what I want to do is I will call this reset state as 0, state 0, one state as, you know, I'll numerical 1, 2 and 3, I'm going to call it like that. So this is my x, this is my state, okay. Obviously you are at 0 here, 0, 0, then you saw a 1, so you went to state 1, then you saw another 1, you went to state 2, but then you saw 0, you came back to 0, then you went to 1, you came back to 0, then you went to state 1, you went to state 2, back to 0, state 1, 2 and 3, and you remain in state 3 and then back to 0. So corresponding to this state 3 alone, we are seeing this output of 1 here, okay. So effectively this is how this sequence detector is going to work, and you will see the output y corresponding to this input in the exact following way. This is a completely hidden thing that, you know, we don't really care about too much, right. There could be multiple ways of implementing it. We might choose the lower area or lower timing, whatever it is, right, but ultimately what matters is this input output sequence must be maintained exactly, okay. So now let's proceed to figure out how we can implement this using D-FlipFlops, JK flip-flops and so on, right. So what I'm going to do is, like I said, I assign states 0, so I said reset is 0, state 0, okay, in binary. 1 is 0, 1, 2, 1, 0, 3 is 1, 1, okay. So this is my effective, you know, state diagram, and now I'm going to go backwards, like I said. So from the state diagram I will move to a state table, right. So for that, let me get this, make a copy of this here, yeah, okay. So let's now write the state table description of the state transition diagram that is shown here. So I'm going to look at present state, input, next state. Okay. So now what I will do is I will redraw this with the appropriate binary codes that we have assigned for the states. Right, and I will also use my color coding that I did earlier 0 0 0 1 1 0 1 1, right. This is my state. My input is going to be in red, right. Sorry, this is 0, this is 1 1 and 0 0 and 1, right, and my output is going to be in magenta. 1 right. So let's look at this. Present state is 0 0, input is 0 0 0 1 0 0, sorry, 0 1 0. No, this will, I'll write this later. In red, I will write the inputs 0 1 0 1 0 1 1. Okay, and my next state, and then I also need an output. Okay, so now I need to be careful here. Yeah, okay. My output y, this is x, and yeah. So the next state is if the input is 0 0 and I am receiving an input of 0 0, then the next state is also 0 0. Right. So remember earlier what we did, right, was to start with the the circuit diagram and propagate the outputs until the input to the flip-flop D or J, K and all that, and based on that we figured the next state. Now we are given the next state, we need to figure out the input to the flops. Really, that's what the story is, right? So what we have here is we have the next state that is given to us. We need to figure out this input here. Okay, that's the basic idea. Okay, so if the present state is 0 0, then and the input is a 0, then the next state is a 0 0. If it is 0 0 and the input is a 1, then you go to 0 1. If you are at 0 1 and you get a 0, you come back to 0 0. 0 1 you go to, and the input is a 1, you go to 1 0. Now if you are at 1 0 and you get a 0, again go back to 0 0. Here you go to 1 1. Right. Now at 1 1, if you get a 0, you go back to 0 0, otherwise you just stay in 1 1, and the output is very straightforward. You are just going to say 0 0 0 0, I mean here 1 0 1, right. That's exactly what you are going to do. So if the next state happens to be a 1 1, then you are done and you will get the this thing, right. So now what we need to do is we need to figure out, we got to first of all pick what flip-flop we are going to use for this particular design. So let's start off with the D flip-flop, right. So I have 2 bits, right, for the states, and therefore I obviously need 2 flip-flops, right, because I need 2 output bits to represent the number of each bit of this state, right. So I have 4 states, I need 2 flip-flops, and therefore 2 bits, right. So what we are saying now is I have a flip-flop like this. Right? This is my DA and this is my A. This is my DB and this is my B. Okay, and I have my clocks here connected like this. So we are trying to figure out what this DA and DB should be. Okay, so flip-flop input DA and DB. So present state, I am going to look at A and B. A and B. So in order to determine DA, I need to just look at this particular column, right? These two columns. If the present state is a 0 and the next state happens to be a 0, right? Then what should my input to DA be, right? That's all I have to worry about. So if I want the next state to be a 0 in a D flip-flop, it's very straightforward. I just have to replicate this guy, because there's really nothing which, it's either set or reset in a D flip-flop. Okay, so therefore this will just be 0 0 0 1 0 1 0 1. For DB again, I'm just going to reproduce this here, right? So 0 1 0 0 0 1 0 1. Okay, so my output is now available, but the input to the flip-flops are available here, and all I need to do now is a Kmap minimization in order to solve this, right? So if you look at this, my DA will be 0 1 2 3 7, yeah, okay. So my DA is summation of minterms 3 5 7. DB is summation minterms 1 5 7, right? And my output is summation minterms, one second, sorry, here my output Y is not, I have to look at the present state, right? If the present state is a 1 1, then I will output a 1. That's all that matters. Sorry. Yeah. So therefore this will be minterm of 6, 7. Okay. So these are my Karnaugh map, related information that I need to use in order to minimize the Boolean variables. So therefore I will do that. For DA, I have 3 variables. Okay. So let us look at it. This is this will be A and this will be B and X. Zero, 1, 3, 2, 4, 5, 7, 6. B bar, X bar, B bar X, BX and BX bar, A bar and A. Okay, so I have now what I can do is, yes, I will make a copy of this and have it handy, one for each flip-flop input and output. So this will be dB, this will be my output y. Okay. So if you look at the dA and dB now, we are talking about dA is 357, right? So you have, let me do the different color, 3, 5 and 7. So I can simplify like this, right? And dA therefore will be equal to, so I have Bx plus Ax, okay. dB is now what? It is summation 157. So 157. So again this is my grouping, right? dB therefore is going to be B in black, B bar X plus, actually it's an OR there, AX, okay. And my output Y is going to be 6, 7, right? That's what I got. So therefore this will be 6, 7, and therefore my Y will be equal to A into B. I think this was a very straightforward thing that we could have guessed already, because when the state is 1, 1, the output is 1, otherwise it's 0. So therefore it simply has to be the AND gate of the two flip-flop outputs. Even when just by looking at this state diagram, we could have told this, right? So therefore we came from the state diagram to the state table to the state equations, and we can go ahead and now implement the circuit exactly, okay. So therefore I have D flip-flop A, B, so I'll call it D1 and D2, D flip-flop, no, I'll just call it FF1, okay, FF2, yeah. So what I have here is I have A plus AX or BX, right? So I'll do this. Right, so X, right? So maybe I will just route this line X like this. Okay, so I have the input. This is my DA, this is my A, and this is my D, B and B. So what do I have for DB? It is B bar into X. So I will assume that Q bar is available here. So it's a very similar. So by the way, since we are looking at AX, which is common to both DA and DB, you could also take that output directly from here. Okay. And this is B. Finally, you go and add your AND gate here and you will get the output Y. Okay. So with that, what we have been able to do is to get the exact circuit implementation also done for this whole thing very well. Okay. So our combinational block 1 is on the left, combinational block 2 is on the right, which is just an AND gate. We use 2 D flip-flops and we were able to. So this circuit effectively will do the sequence detection of 3 ones for you. Okay. Now you could do many more complex sequence detections as well, right? You could look for a particular sequence of 11001, if that has happened or not, right? All this is very much possible. You just have to systematically construct the state diagrams and come one by one and then implement it with the flip-flop, right? So the D flip-flop is the most common flip-flop that is going to be used in the industry for all these kind of implementations in state diagrams. It is not done using manually like this. It is done using languages like Verilog and all that. But in order to even code in Verilog, in a hardware description language like Verilog, you need to have a very clear understanding of the hardware, which will come only if you practice this nuts and bolts level stuff right now. Okay. So this is the building block for you to be able to do digital design well in future courses.